Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody watching us from the future. So we continue today on cloud storage. The screen is a bit bright, I'm not sure why, so we just took pictures and we'll let technical support know, and maybe we'll find out why that is. But can you still see if I project? Yeah, all right, very good. So I'm going to start with a question because we are using a Docker installation to ease things. That way, no matter what operating system you are using, it should just work. This Docker contains PostgreSQL, contains Spark, contains RumbleDB. It will also contain the exam environments of previous years. And we'll also use it for most exercises. Not all of them, there will be other Dockers, but for many of them. And so I would like to have an overview of how this is working out for you. So for many of you, it perfectly worked. For some more of you, it didn't work immediately, but switching it off and on again worked. Then we did have the TAs jump in. There was one case of a full disk that was solved, and now we know for the future what command to use. Some of you haven't tried it out yet, so I encourage you to do that. And for those of you who have issues and need support, drop us an email, write either in the Moodle forum or in the Element chat. You can directly let us know your operating system that you're using, if you install Docker Desktop and not another edition, if it's an old version of Docker that you installed long ago, or if it's a fresh version. What else could we need? Check if your disk is full, and send us a screenshot of exactly the error you're getting, right? And then we'll jump in to help you. Okay, so that's two of you. This is all under control. Out of curiosity, who tried out? This is, of course, something else and completely optional. Who tried out pip install JSONic, just like that? I know at least some of you wrote me an email. Yeah, awesome, wonderful. This is optional, right? But I'm really looking for feedback because this module is very recent during the summer. And right now, we would like to know about all the errors that people get so that we can have informative error messages. But of course, if you use the Docker, then we expect that everything should just work. All right, very good. Something else that I wanted to tell you is about those of you who had a VECRA. Let us know, send us an email to me, to Tikai, and we'll see about a solution for the bonus points, the quizzes. So in particular, the 6 of you last week who said that they are worried about the bonus quizzes because of the VECRA, right? So drop us an email and we'll try to help. So now I'm going to continue where we were. S3 did not document how they built it. So I'm not able to tell you what is happening on the physical layer. However, since the other cloud providers have similar services and they let us know how they did it, in particular the Azure blob storage, they told us how it's possible to do it. So the paper is linked on the Moodle page, and so you're encouraged to read it. There's a few details, right? But on the high level, very quickly, what I can tell you is they use so-called storage stems. So that's basically, think of a room in a data center with plenty of computers piled up in, what is it called? When you pile up the computers, it's a rack. Oh, by the way, there is a rack right here. If you want to come in the break and look at it, it's not actually computers here. It's more like audio, video. This is a rack. It looks exactly like what you have right here. So you have rooms in data centers filled with that. They call them storage stems, this full room. And it's about 30 petabytes of data that you can fit in there. And the goal they have is to keep it below 80% of storage capacity. If it exceeds 80% of storage capacity, then they will start offloading it to other storage stems, because of course they don't have just one, they have plenty of them all over the world in many geographic locations.
Rob, yeah? There's a question on Zoom. Are directories in S3 also objects within a bucket, or is it only the files within these directories?
So it's similar to S3. I'm talking about the Azure Blob Storage, right? It's similar to S3, but they don't have just the bucket and the object. Instead of just these two levels, they have three levels. The first level is the account, the name of your account. So this is something Amazon doesn't have. And then the equivalent of a bucket ID, but within the account. So for them, it's possible to have the same bucket ID across different accounts, but they don't call it buckets, they call it partition, I think. So you have the account ID, the partition ID, and then you have your object ID. Actually, I had a slide that was showing that, and I have no idea why it disappeared, because that was supposed to be the slide right before that. Maybe if you give me a few seconds, I find a way to bring it back to life. So there you go. Oh, it's actually right here. I just jumped over it. So let me project it again, and then I can show you. There you go. So you see it right here. You have buckets and objects in S3, and in Azure, you have the account, the container, and the blob. Partition is a synonym for container that they might be using in the academic paper, but then when the product was released, they called it something else, right? So I think the official documentation now says account, container, and blob, right? So it's the same, except that instead of 2 IDs, you need 3 IDs, right? And the container ID is only unique within an account. For whom is that clear? Right, very good. Now, in terms of the API, something that I haven't told you about S3 is that even though the object is a single big black box, right, just a set of bits that you upload, if you try to upload a 5 terabyte object, that might be a bit tough. I don't know if you already made the experience, but typically if you try to upload very large documents, there is some chance that there will be a network issue and it just breaks in the middle and you have to do it from scratch. To whom did that happen? Right? It does happen over the network. So it's actually challenging to upload data that is terabyte size. So there is something for convenience, but it's only in the API. It's not part of the models, just in the API. It lets you upload the object in parts. So you can upload, instead of 1 terabyte, for example, you can upload 10 times 100 gigabytes. And then at the end, so you say, okay, this is part 1, this is part 2, this is part 3, and so on. And then at the end, you do one last instruction to just have the server assemble them into a one object, right? And then you have your object. So these are called parts. And again, it's only part of the API to upload object as a convenience to do it in multiple stages. Now, in Azure, they actually go an extra mile in terms of what they offer. And in fact, what Azure offer is already almost what we will see next week, right? Because they go beyond. So they have several kinds of objects, let's say. They call them blobs objects. You know what blob means? Binary, large object, right? So they call it a blob. And a blob can be a block blob, an append blob, or a page blob. The ones that we are most interested in for the purpose of data, big data, is the block blobs. Right? So these are objects, but they make what would be the parts here are made explicit in Azure. Right? So you actually have all the objects that you store in there. In the Azure Blob Storage, they are explicitly cut into blocks. We'll see that this is what happens in Hadoop, and in HDFS, the blocks are also exposed to the user. So this is why I'm saying they went an extra mile, and they are almost, a distributed file system in the sense of what we'll see next week, right? And again, in S3, the parts are not the same because it's only for uploading. It's only for uploading that you can cut it into parts, but once it's uploaded, there is no more notion of part. For whom is that clear? All right. So just so you know that, and the blocks, don't worry, we'll see next week what the blocks are about. The append blobs is a different kind of object that is meant for logging. It's basically when you have sensor data or you accumulate the logs of your website and all you ever do in your objects is you append something at the end. So they do have a way to do that, a special kind of blobs that is just implemented differently, and this one is optimized for appending. And then you have yet another kind of blob called page blobs. These have to do with virtual machines, like EC2, but on the Azure side, and so they use the page blobs for handling some kind of virtual memory for the machines. So append and page, you don't need to worry about it too much. It's really the block blobs that we are the most interested in. And then in terms of limits, you can see it's a bit different because we have 5 terabytes. Remember, 5 terabytes is what I told you last week for S3. And for Azure, they have different limits, and it depends on the kind of object that they have. So for blocks, they have an incredible 190 terabytes of limit. Why? That's because of the blocks. Because since they cut them in blocks, then the blocks can be small, and then they can have many blocks. So this is why with blocks you can achieve more. Again, that we'll see next week, how you can achieve more with plenty of blocks. Then the append blobs for logging is much less. It's 195 gigabytes. Again, that's just like sensor logging, website visits, loggings, and so on. And then 8 terabytes for pages, which sounds reasonable because it's, again, virtual memory for virtual machines. All right, so this is just to contrast the two. We have a question over here. Maybe we can, we don't have a cube. What do we have for questions? Oh, there are no microphones in there. What we can do is you could ask your question and we'll repeat. We'll just get closer. Go ahead.
Like in the blocks and pages, like the 190.7 terabyte, it's like the total space a block can have within an object ID, or it's like the space of, that's the limit of one block, like how large?
The total blob, the total object. Yeah.
And like between block and page, like the difference, because like in my opinion, if we are storing both on like the hard disk or like the like SSD, it's the same. So it's like page is stored on a faster accessible memory. Is it like that?
So the pages, I think, are much smaller than blocks. I would have to look it up. I can look that up and get back to you on how much it is. But one page would be very small because this is really something that has to do with memory, right? But the blocks, they are much larger. I can actually tell you what size the block has, and then I'll see if you remember next week when I ask you how large a block is. So a block is basically hundreds of megabytes or maybe a few gigabytes. That's the size of one block, right, of data. Hadoop is 128 megabytes, and I think Azure uses 4 gigabyte blocks or something like this. But a page is much smaller than that. I don't know it by heart. I will get back to you. All right. Yes, go ahead.
Sure. This person wants confirmation that the data uploaded stays in block form, unlike S3, when parts are only used for uploading. Is that correct?
That is correct.
Okay.
In S3, you can upload your object in multiple parts, and then you glue them together, and then it's forgotten where the parts came from. But in Azure, the blocks are explicitly part of the API, so you upload blocks and you can read blocks also, right? Does it answer your question? All right. Did I also answer your question? Awesome. And I'll get back to you. Could you please make a note to get back on the size of the pages and so on? Thank you. All right. Then we have, I told you about those storage stamps. And then what I can also tell you, one last thing on the high level, an insight that they give us. And again, maybe Amazon is doing the same thing on S3, I don't know. You know that, you remember what I told you about you could lose objects. So then you replicate and you store multiple times. So they do the same. In Azure, they store the same object, the same blob, multiple times within the same storage stamp. This is called intra-stamp replication. And they also store it in another storage stamp, just in case there is a fire in the first one, and then they still have a copy somewhere else. So they have inter-stamp replication. What do I mean with synchronous, asynchronous? I mean that when you upload a new object or new blocks, it replicates them on one storage stamp, but you have to wait until it is done. So if you try to upload an object, it's blocked. The code is blocked until it has been replicated. But here, it doesn't block you, meaning that this replication right there can happen after the call has returned of the upload, and then in the background later it's going to replicate to some other places. Who is with me? Okay. And again, the reason we replicate the data, there's two main reasons. One of them I told you is resilience to natural catastrophes. If there is a fire or an earthquake somewhere, then you want to have your data at other places. And this is real life. It happened. A few years ago, there was a fire in a data center in eastern France, and they didn't back up the data, and that actually caused a lot of trouble for the businesses who had their data there. So it's very important to replicate. The second reason is latency. Remember latency? I told you about last week, the time you need to wait to get your data. When you visit a website, you like it when it's fast, right? When it responds very fast. But if you only have servers, let's say, in the US, and you have customers all over the world, then the customers in Asia are going to have more latency because it's the speed of light, right? And it's even slower than the speed of light, the internet. For this reason, what many companies do that have worldwide users host a copy of their website or a copy of the code for the website also at multiple locations. And when you connect, it's going to connect to the nearest location. So that also optimizes the latency. So these are two reasons for replicating. And again, I'll tell over the lecture, we'll keep replicating. That's how you avoid data loss. So that's it for Asia. You should read the paper that I told you about. Good insight into how it's done. Regarding the blocks, don't worry. The blocks we'll look at next week with AGFS, and I'll tell you more about them and how the API looks like. So, any questions so far? S3, yes, I see your question over there.
What happens in that case? Is it the fault of the host or the company?
So I'm not sure about the details that happened in that very case. It was basically in the news. Probably there was some legal disputes, and there are arguments that can be made that the data center provider should have put it at other locations. But you can probably also make arguments that depending on the agreement that they have, it could also be that it's the customers that should have replicated it to other places. So I guess this is something they argue in court to decide the responsibilities. And that probably depends on what is in the agreements and the service level agreements. But I don't know the details in that specific case of what happened. Right, but it's an example for everybody else that you really need to replicate. And so probably as a cloud provider, you should replicate to avoid data loss, and then you can make the guarantees to the customers. And then as a customer, it's also your responsibility to check these agreements and to understand in which locations your data is sitting, right? Of course, there is another aspect, which is that the law might forbid you to store your data outside of your country, right? This might be the case for banking data in Switzerland, for example, and that restricts where you can store your data. This is becoming more and more important today. But within Switzerland, you could still have something in Geneva, something in Zurich. You can diversify a little bit, right? Does it answer your question? Okay, all right. We could actually, if you mark it, we could also try to investigate what happened in the case if it was the cloud or the customer. And of course, what you see in the SLA, the service level agreements that give you a probability of loss, is based very likely on this, on how much they replicate, and in order to ensure a specific SLA. Mm-hmm. All right. So now we'll move on to something slightly different, that is key value storage. So now you're going to tell me, but we already saw key value storage, because in the object storage, we have IDs and we have objects, and that's it, right? Even though the ID might be made of bucket object or account container object. So you might tell me we already saw that, but actually we didn't, because when people say key value store, they don't mean the same as object storage. They don't mean the same as cloud storage. When people say key value store, they mean something a bit similar, more similar to a database with a very low latency. In a key value store, you expect a few milliseconds of latency when you get your object. In a system like S3 or Azure Blob Storage or HDFS or all of these systems, the latency is going to be maybe 100 times more, hundreds of milliseconds on average. It takes a bit more time. And of course, that's not good or bad. It's just that these are systems that are optimized for different things. Because in the case of S3, you can store very large objects. The same is in Azure Blob Storage. But in key value stores, in typical databases, you store something smaller. So I think I have it here, yes. So instead of up to 5 terabytes in Dynamo, which is the example we are going to take, the objects can be up to 400 kilobytes. Much, 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 much smaller, right? So that's basically the difference on a high level. But what's interesting is if we look a little bit into them, because they were, again, very trendy 15 years ago, where everybody was rushing to get their own key value store. So we look at the API, and I'll tell you a little bit how they are implemented. Just so you know why that was such a buzz and such a trend, that has to do with the CAP theorem, because you might remember that I told you can't have C, A, and P, and in the case of a network partition, you have to choose either you're available and you're not consistent. And in fact, when the first engineers decided to not be consistent and to only remain available, but you drop consistency, so you can actually deliver different results to different people, that was a big revolution. Right, it was almost provocative, right? That you would build basically an unreliable system because you might return different results. But in fact, the reason it worked is that there are use cases in which that makes perfect sense. And there is an example of that you might have noticed on social media. When you upload, you write a comment somewhere, then you refresh and your comment doesn't appear. Then maybe you will see it a few seconds or a few minutes later. Who noticed that sometimes? It has to do with this. That has to do with the fact that you drop consistency. And so when you again access to try to see the page with the comments, you might access a different place that doesn't have yet the propagated update of the comments. That is called eventual consistency. Who has heard of that? Right, eventual consistency. Eventual consistency, if you express precisely what it means that if you completely stop updating anything and you just wait, then at some point, it will all be consistent and it will have propagated everywhere, eventually. But the fact that this is assuming you stop the updates is important because if you, and that's what happens in real life, you keep updating and updating and updating, those people use your website, then it's never going to be consistent, right? Because there's always updates and updates and updates that haven't propagated yet. So this is what it means to be eventually consistent, right? You drop consistency in the CAP theorem, so you are AP. So this is an AP system, the key value store. All right, and of course, the benefit you get is even if it breaks, it remains available, very low latency, and so on, right? Okay, so what's the API? Very, very simple, get, put, and delete, of course. That might remind you of REST, by the way. We've already seen that in REST. That's a pretty basic API, I would say very low-level API in big data. So you can get an object or a value associated with a key, or you can put a new value associated with a key, or maybe create the key and associate a value with it. Now, in fact, there is also a context, but I'll say more on that later. There's an additional parameter that has to do with the eventual consistency thing that you need to maybe solve conflicts sometimes. So just to contrast, normally in database systems, you expect that everything is consistent. You have a lot of features, a query language, ACIDs, you have a lot of overhead, you're monolithic, right? Just drop it on a machine and use it. But now, and this is the spirit of the rush into big data, we simplify things. We are eventually consistent, AP, very low latency, performant, and scalability because you can have a lot of machines, right? So the early systems went on that side. Now, what is the logical model of a key value store, but also of cloud storage or object storage? That's just a key value model, and that is known as an associative array or as a map right? So if you take the abstract data type, that would be a map from keys to values. We'll see these all over the place in the lecture. There would be maps like that everywhere at all kinds of level. This is at the physical level. This is really a system that fundamentally at the low level associates values with keys. It's buzzing. Maybe it's the battery is complaining about the battery, or maybe that I'm far away. All right, so key value stores, very low latency. It's not on a single machine, it's on plenty of machines, right? You have a data center, you have plenty of computers. And something very important is that computers come and go. So you might have a new computer that joins, and you might have a computer that crashes or that gets out of service and it's removed, right? So it has to be resilient to that. You cannot just stop it and tell your users that it's no longer working because of availability. So you have to continue to work. Another principle is symmetry. Symmetry means that you don't have a centralized architecture with one computer that has a different set of responsibilities than the rest, at least when you start. So it's like a democracy. Everybody's there, all the computers are there. They might elect leaders or elect some computers to do some things, but at the very start, all the computers are equal. But it doesn't mean that all the computers have the same memory and CPU and so on. They might have heterogeneous features, not the same disk space, not the same memory, but they are like in a democracy where there is no particular computer that is singled out from the others. So it's completely decentralized. That would be a peer-to-peer architecture. All right. And then again, I already said that, but they don't need to have the same number of CPU cores, the same memory, and so on. So you might have computers that have more and computers that have less. Peer-to-peer, meaning they all communicate with each other, right? Not centralized. And that's how it works, because that might seem challenging. Like how do you build that sort of things? Well, the trick is that you implement this map, because in fact, logically it's a map, with what is called a distributed hash table. Who heard of a hash table? Many of you, right? Like for hash indices. Well, this is a hash table, but it's distributed over multiple machines. So the way it works is we take the keys, so the keys that you want to associate with the values, and you hash them. What it means to hash them is you put them in some cryptographic function that is a hash function, and a hash function basically produces something that looks random except that it's deterministic, right? So it basically produces bits that are very hard to predict, but it's always the same bits for the same key, right? So it's stable. So every key gets hashed into a 128-bit ID, 128 zeros and ones, yes?
Does it have to be cryptographic, the hash function?
I just use the adjective cryptographic to mean that they come from the cryptography area. They are discussed for encryption and so on. But of course, here we don't encrypt anything, right? So that's not the way I meant the cryptographic adjective, right? I'm just connecting to the same that the sort of hash functions you would use are the same hash functions that you would have in cryptography, right? Does it make sense? All right. Okay. So 128 28 bits that look random, like you cannot really predict what that is. And now if you look at these bits, these 128 bits, you can, it's a modulo thing, right? It's basically a ring structure in math, Z over NZ. You might have heard of this in discrete math. So you can look at it like this circle, right? Where you start at 0, 0, 0, 0, and then you count in base 2 all the way to 2 to the power of 128 minus 1, and then you're back to 0, right? So essentially, when you hash your keys, what you're actually doing is that you're randomly placing the keys on this big circle, right? This is what's happening. So the keys that you're going to store, when hashed, they are on that circle. The next thing you're going to do is the same with the computers. You're going to create a hash for every machine. You can use for that some random stuff, some states of the memory, some CPU, the time, the date, like whatever you have to create a hash for every machine. And again, that places the machine logically on that, on that circle, right? When you hash every machine. Who is with me? Right? So this is when it's decentralized, you can do that. And thanks to the power of something that seems random, you've basically placed them roughly well distributed on this circle. And what's next is the responsibility. The idea is that all the keys that get hashed to this zone are the responsibility of this machine. All the keys here are on this machine, all the keys here on this machine, all the keys here on this machine. So by hashing the keys and hashing the computers, you've actually managed in a completely decentralized way to assign responsibility of keys to the machines, right? That's the magic of distributed computing and peer-to-peer networks. So that's the domain of responsibility of this machine. Now, what happens if you add and remove machines? Because I told you it has to be resilient. Well, let's say here, there's this entire domain that is stored here, and we add a machine. What's going to happen? There is a transfer of responsibility. Basically, all of these remain on that machine, but the keys now that are here, they used to be on that machine, they are transferred to this machine right here. Who is with me? Right? So you can add a machine like that, and that shifts the responsibility. And likewise, that doesn't affect the other nodes. Very important because that's local. That's only a local effect of adding a machine on that logical structure, this logical circle. What if you delete a machine? Like imagine you have these keys here. You delete that machine. Elegantly, not a crash. It just gracefully shuts down, and even one in advance is going to shut down. So what's going to happen is that these keys that used to be here are going to be transferred here. If it crashes, then that's a problem because we lose the keys, but we are going to solve that now. So what if the node crashed? Well, the trick is that instead of storing the data, the key, each key on one machine, you store it on multiple machines. Again, replication. So what we say now is that a computer is not responsible just for the range of keys that precedes it on the circle, but we are going to say a computer is responsible for the next 2 or the next 3 ranges, right? Like this. So this computer, for example, would store not only the keys here, but also the keys here. And what that means is that the keys here, for example, would be stored here and would also be stored here. Who is still with me? Yes, there was a question over here. Mm-hmm. So the problem of the solar machines, we'll also solve it later with a trick, with tokenization. Why don't we just assign them? Well, that's because you have to add and remove machines. So if you just assigned it manually, imagine you find some protocol to do that, then when a new machine joins, you still need a way to assign on the circle. And somehow the hash function is the simplest trick that you can find to just make a decision. Right, just you decide sort of uniformly at random on the circle, right? It's basically you could maybe come up with some fancy algorithms that have strategies for placing the machines. I'm not sure you would get an advantage over just using a hash function. That might be, but I think the hash function is probably the simplest you can think of. Yeah. Does it make sense? Yeah. All right. Okay, so it can be 2, 3, so that's a parameter, right? Let's call it big N, uppercase N. Now, what we have is something we call preference lists. Every computer knows basically for every key that there is, the nodes that are responsible for it, right? So for example, the key A is stored on nodes N1 and N2, if we number them. So this is called a preference list, right? So it doesn't have to be physically in that structure. Maybe you would have, instead of the keys, you would have ranges of keys, right? But basically, you know, for every key, instantly, you know which nodes are responsible for it. This is an innovation of Dynamo to do it in this way, because in the original distributed hash table system that is called CORD, they didn't do it in this way. They called it they did it with a binary search, meaning that they jump by a large distance, like when you want to look for a key. they just go to some place, and it's not there, then jump by a large distance, then they're too far, then they go half of it, and then again half, again half, again half, again half, and then in a logarithmic time, they locate the key, right? Who agrees with that? That's a binary search. This is O of 1. This is not O of log n or of log of the size of the entire number of keys. This is O of 1, right? So this is an improvement in terms of complexity. But there is, and I'm not entering into the details of how this is stored, because you need some distributed system protocol that organizes the synchronization of this across all of the machines. Think of the blockchain, right? The way that the blockchain is synchronized also on a peer-to-peer network on all the machines that are in the Bitcoin network, little bit similar. So there is a way with some distributed system algorithms to share that information, right? I think it's called the gossip protocol, if I correctly remember. All right, so every node knows about the ranges of all other nodes, O of 1. And then in terms of parameters, I'm going to introduce you to two more. You already know n. N is the number of ranges that every node is responsible for. That's also the replication factor. We also have R and W. R tells us whenever you want to read the value associated with a key, you have to communicate with at least R nodes. And then you get the values that they have. Maybe they'll all agree, maybe they won't agree. But whenever you read, you at least need to communicate with R nodes. When you write, you at least need a confirmation synchronously, meaning it's blocking the call when you do the put. So when you put, you need to wait for at least W nodes to confirm that the write was successful. And you can pick R, W, and N for your system, but you have to pick it in such a way that R plus W is greater than N. That's a condition of the system, right? And so the way the system works is that when a client wants to communicate with this system, wants to communicate with the key value store, they will connect with some random node, how with a load balancer, similar to the internet when you have a large website that randomly assigns you to a server when they have millions of people using it. So you connect to some random node. The random node is going to forward you to the coordinator node for that key. It means that it's the main computer in charge for the range in which the key is, right? It's the closest one. And that coordinator is going to handle the request, and it's going to communicate with all of the other nodes that host the key as well, n-1. Who is with me? All right, so these are the n-1 nodes that precede it on the ring. Okay. So now, there's good things and bad things about that system so far, the way we've built it. It's highly scalable, can have a lot of machines. It's robust against failure, because if a machine crashes, even not gracefully, if a machine really crashes because we replicate it, it's all fine. It's self-organizing. That's an aspect of the hash function, right? Self-organizing. But the problem is, and this one we won't solve, you cannot search, you can only look up. You cannot have a range of keys that you want to check. You need to know which key you want, and you specifically look up your key. Why? Because there's a hash function. So if you have an interval of keys, and you take the hashes of all these keys, they will be all over the circle, right? So the hashes do not preserve the range of the keys. For whom does that make sense? Right? Okay. And there are security aspects also, but it's not a security course, so I'm not going to tell so much about it. But there's all kinds of ways with authentication and to make it secure. But some of the issues that we are going to solve is issue number one, poor distribution, and that's kind of the question also that you asked at the beginning. What happens if we are out of luck and we end up like this, right? And with one computer responsible for a huge range and then a few others for less. Second problem, they might have less or more memory, right? So how do you handle this? Because you would like the ones with more memory to be responsible for more keys than the others. So here too, it's very heterogeneous, but the hash function distributes uniformly on the circle. So that's also a problem. And the answer is tokens. So what we are going to do is virtualize, just like we have virtual machines, now we have virtual responsibilities. So we are going to, let's say, if you have 100 machines, we are going to create 1,000 points on that circle, right? So now these points are no longer machines, they are just a virtual responsibility. And then we assign them to machines. Imagine I have 6 machines here with the colors. Every machine has a few of these tokens. This one, the yellow one, for example, is responsible for this. So it would be this range right here, plus a few others, plus this right here. So it would be this. The green one, this, and so on, right? So you have tokens. So you have many more points on the circle than there are machines. And then the machines just are responsible for some of these. Who is with me? Right? So now what happens if you delete a machine? Well, yes, you can delete machines in the cloud. That's actually quite cool. Not just shut it down, but completely delete it. By the way, never forget to do that. When you launch a machine in the cloud, do not forget to shut it down because then you receive a very huge bill at the end. It happens sometimes, even here at ETH. Then we write them an email, oh, please, we're academia, we made a mistake, and so on. And so they say, okay, but don't do it again. But yes, so if we delete that node, we need to reassign the tokens to other machines, right? So this is how we handle it. And if we add a node, then we just transmit some of the tokens to that node. So that's how we add and remove nodes. But now we're mitigating the thing because the computers that have more memory, they will have more tokens, and the computers with less of a configuration, they will have less tokens, right? So that actually solves a bit the problem. Looking at the time, I have 5 minutes left, so maybe I can still start a little bit of that. Actually, something that was invented at ETH by, I think, Friedman Mattern, who was a professor in the department. Here it is. When you have a system, let's say you have only one machine, and you're the only user, and you're updating the database. Do you agree it's linear? It's a line, right? If you would have versions, that would just be a line with all of the versions that are consecutive. So you have version 1, version 2, version 3, and so on. The problem is that in our case, you might have network partitions and all of that, and you might be not consistent. So it means that if you forget about the characters written, but only look at this, you might have version 1, version 2, but then because of some conflict or network partition, you might now deviate to a version here and a version here, but these ones are not comparable, right? So it's no longer a line, right? Who sees that? All right. And so the idea of vector clocks is that instead of using numbers as we would for a linear, just a sequence of versions, we use vector clocks, which are vectors of numbers. So basically, we associate every machine, every token, with a version, but that version is specific to the token. Whenever a token sees a new version, it increments its counter, and then you have one counter for every one of the machines. So what happens here is that node A saw a version, updated it, then node A saw it again, increases it to 2, A2. Then it's node B, maybe because of a partition that processes the request, but then it increments its counter. So B0 was implicit, now it's B1. And independently of that, maybe on some other part of the network, then C creates another version, a yellow square instead of a red triangle, and has C1. These are the vector clocks. It's a little bit like some special relativity, right? It's as if like B was on the Earth and C was on Mars, right? So there's kind of a link with special relativity. But this was the solution invented at ETH to replace just numbers with vectors in order to handle the versioning and keep track of what is before what in terms of versions. Next week, I'll start with an animation to show you how that works in details, and we'll have a series of gets, puts, and then see how that all works. So we are going to finish here for today. Again, we are here to help if there's anything, send us an email. There is an exercise session for the first time this afternoon, and I hope you will enjoy it, right? So brush up all you can on SQL because we'll use SQL later in the semester and at the exam. Thank you very much, and have a nice day.